Our next speaker, if you were here last year in Dallas at the Mars Society Convention there, Ashwin Vasavada was there to talk about, in a year's time, this mission that we all know very much about now was on its way to Mars. Well, it was just going to be launched, actually. It was in November of last year it was launched, and of course the convention was in August in Dallas. So there was a lot of excitement around this mission, and when Ashwin said, you know, in a year's time we're going to be excited for this day, well, this day is here. So we're very honored to have him back with us, and he's a very busy guy. I'm sure all the guys in JPL are just going nuts at the moment. So thank you very much for coming, Ashwin. He is the senior scientist at NASA's Jet Propulsion Laboratory, and he's deputy project scientist for the Mars Science Laboratory Curiosity. He's going to host a question and answer. He's got a little bit of an introduction to do first, but then he's going to invite questions from you guys. So let's think of some good ones. Over to you, Ashwin.
All right, it is good to be back here at the Mars Society Convention. Can you believe it? Tomorrow night. Yeah, exactly. Yeah, so I've been working on this mission now for over 8 years, and started when there was just maybe 50 people at JPL thinking about this mission before Spirit and Opportunity even landed. And then since then we've grown up to about 1,000 people at JPL, mostly in the engineers, a few of us scientists hanging around to get the experiments in order. And now we're at the point where we've launched it successfully. We're coming down, you know, speeding up actually every second as Mars gravity tugs us in as we get closer and closer. And we'll enter tomorrow night about 10:21, oh, what is it? 10:24 Earth received time. We'll enter the Mars atmosphere, and 7 minutes later be on the surface. It's all getting kind of surreal. I've lost my voice already, just talking with all of the wonderful people that are so interested in this mission. We had no idea what to expect in terms of public support and media interest, but it really has exceeded, I think, all of our expectations, which is really good for everybody, you know, that cares about Mars and space exploration. We've had incredible coverage, and 400 reporters are expected to descend on JPL tomorrow night, and 15,000 people, including yourselves, thank you, are in Pasadena, filling up every convention hall and every university auditorium and every single room that holds people at JPL. So this is going to be a great event, and just can't wait, actually. So I can tell you all kinds of different things. I didn't want to give you slides. I think you probably all know a lot about Curiosity at this point. So I think maybe the best, most enjoyable thing for you might just be to ask questions, and I can just ramble on and tell you everything that's going on. And I can tell you about the entry system. I can tell you about what science will do on the surface, how we'll operate the spacecraft. Anything you care to know, I can at least try to give an answer. Maybe someone could help moderate too. That'd be good.
Okay, who's first?
Then I don't have to show favorites.
Yes, sure. Yeah. Guy in the green.
I would like to know, if you find organic carbon with your SAM instruments, how will you test to see if it's biological?
Yeah, good question. So one of the things that has defined Curiosity from the beginning, as you know, the mission's really formally called the Mars Science Laboratory. And so the whole reason we're so big and the whole novel thing we do with the spacecraft is bringing a laboratory to Mars. And the SAM instrument, the Sample Analysis at Mars Suite, is a mass spectrometer, gas chromatograph, tunable laser spectrometer, all in a box about this big. Normally would fill up an entire room at a university laboratory. And it's specifically designed, among other things, to detect long-chain organic carbon molecules. These are the kind of things that life could use as raw ingredients, as well as the byproducts of life. So this is going to be a spectacular experiment. We haven't done anything like this since Viking, and in fact, this is a much more capable mass spectrometer than Viking, as well as the gas chromatograph, which is when you flow the gas through these long tubes, they separate out the organic molecules, and you can detect each one. So to get to your answer, If we were to detect organic carbon on Mars, especially larger organic molecules, this would be something that has never been done before. Then we'd have to ask the important questions. Where did it come from, and what are the implications for life? There's a lot of debate right now about organic carbon on Mars. You should expect some of it, you should expect carbon at least, to be present just in the rocks and soils like it is on most planets. You should also expect that some of these even bigger organic carbon molecules could come in from space. We now know that bodies flying around in space have some of these molecules that look just like the kind of things you find in our bodies. One of the ways we would help distinguish between different sources would be the isotopic measurements. So not only will we look for the kinds of molecules that we would in the mass spectrometer, but we can also look at the isotopes of carbon, hydrogen, oxygen, other things like that. And we all know on Earth that life tends to use the lighter versions. When it has two versions of different molecules, it likes to use the light isotope version. So life tends to concentrate these lighter isotopes. Now, on Earth, you can maybe make a definitive statement if you see a very light signature in different isotopic records. But that's because we have this giant ocean and rock record as a baseline. On Mars, we don't actually know precisely what that baseline is. So if we were to find something that looks very light compared to things on Earth, we'd have to then understand what it's relative to on Mars. So it's actually a very hard question, and that's hopefully you're getting a flavor for that. That's probably the most challenging thing we've set out to do with this mission, is not only detect the organic carbon, but then say something meaningful about what it means. So, I'll leave it at that, but you'll see this unfold. It's actually a very rich scientific question.
How far do you suspect it'll take to get to the mountain ranges?
Yeah, good question. We are landing more accurately than any previous mission. Another thing we decided from the beginning was to have a system that allows us to land in an area today only 7 kilometers by 20 kilometers. This is compared with 100-kilometer size safe landing ellipses of previous missions. So what's nice about this is we wouldn't even be able to go to our landing site at Gale Crater with the Mars exploration rovers, or with Viking especially. It would just not even fit within the crater. So because we have the small ellipse, we knew from the beginning that we could have a chance of driving out of it. Now the Mars exploration rovers have driven more than we ever thought, and they've actually left their ellipses also. But we planned from the get-go to put our ellipse next to something much more dangerous than we'd ever risk landing on. And one of those things is the mountain inside of Gale Crater. And so we have at least, if we were to land in the very center of our ellipse, we have at least 3.5 kilometers to go in the short dimension of the ellipse, a few miles. But more likely we'll land somewhere in that 7 by 20 kilometer ellipse and then have to drive maybe 5-10 miles over the next maybe 6 or 9 months until we hit the bottom slopes of Mount Sharp and then start driving up all those layers that we're really interested in.
What time tomorrow night do you think you'll know for sure whether you have a lander or a crater?
Yeah. None of these questions have short answers, so sorry about that. The real way to answer that is that the more successfully we land, the earlier we'll know. So we actually have 4 different ways we're communicating with the spacecraft as we're going in. Starting with maybe the least good to the most good, we look directly from Earth with the Deep Space Network. The problem is that we're landing kind of just on the horizon or the terminator of Mars, and Earth sets from view of the spacecraft about halfway through the descent. We may confirm that the parachute has come out, and then the spacecraft and everything with it will kind of go behind the horizon as seen from Earth, and we'll be depending on the other 3 methods. The next method would be the Mars Express spacecraft, which is the European spacecraft. They're going to be recording all of the telemetry from the spacecraft, but won't be able to play it back for a few hours. And then there's the Mars Reconnaissance Orbiter. They're also going to be flying directly overhead and recording everything that we send out, but again, won't send it back till they pass by, come around the planet and back in view of Earth, and then send it maybe an hour later, and it takes maybe an hour or two to then piece that data back together and decode the telemetry. So now, the best way is the spacecraft called Mars Odyssey, which is now a 12-year-old spacecraft, but working great. And it does what's called bent pipe transmission. So it looks at the rover, gets the telemetry, and right away sends it to Earth in real time. And so we'll get, if Odyssey works, if MSL's antennas work, if the landing goes perfectly successful, or even mostly perfectly successful, we should get that telemetry from Odyssey all the way down to the surface and then for a few minutes. And then at 10:31 and however many seconds, you'll know when you see us jumping up and down. Otherwise, if something goes wrong that's not fatal, we may know in an hour, in 3 hours, the next morning. And as my project manager said this morning, if we don't have a positive sign for you within about 24 hours, then we're starting to get pretty low on the survival probability.
Over there on the blue.
Yes, on the Mars Exploration Rover mission, images were made available to the public pretty much as soon as they were received. Is there going to be a similar policy on the MSL mission?
Yes, NASA really has a NASA-wide policy now. So Cassini releases their images in real time, Mars Exploration Rovers, and we'll do the same thing. So we have 17 cameras on MSL. 6 of them are spares, and the other 11 are working all the time. And there's only one caveat, I guess I'll tell you, is that the engineering cameras, the hazard cameras and the navigation cameras, which are the same exact designs on MER, the Mars Exploration Rovers, will be put on the JPL website as quickly as we get them. The science cameras are all run by a company in San Diego, Malin Space Science Systems, and their website will be the first to show their images. But NASA then will mirror their site within seconds, so it doesn't really matter. But you can go to Malin Space Science Systems, msss.com, and read all about the science cameras. They run 4 of the science cameras, the 2 main eyes, and the camera on the end of the arm, and the descent imager. So I think you're all aware, but this is one of the most exciting things I can think of is in the next week, we should have basically a kind of like a YouTube video of the last mile of the flight of the rover down to the surface, as seen by a camera mounted looking down. So from the moment the heat shield comes off down to the surface, we'll have a video that we should have all the frames down within a week or so.
So how do you plan to definitively resolve samples on the Martian surface without a rat?
Yeah, so the rock abrasion tool, which is on the Mars Exploration Rovers, which is a tool at the end of the arm that scrapes away the outer surface of the rock. That's useful because these rocks, especially in the age of Mars that we're interested in, 2, 3, 4 billion years ago, which seems to be more Earth-like than the present-day Mars, if you set a rock on the surface for that long, it can get coated by products that kind of precipitate from the atmosphere. It can get radiation damage at the surface. All sorts of things make you want to scrape off that surface and then see inside. Also, geologists like to polish a rock and get rid of the outer, roughness in order to get a nice clean surface. So the rock abrasion tool on MER was very good at that. Now we had one for a long time, and this is a good story of what it takes to put together these complex spacecraft. My job for 8 years really has been to deal with these decisions where we have trades. You can't do everything. You can do, sometimes you run into something that is so complex that you have to start making your job easier in order to make sure you get it done and launch to Mars. And so one of the things we did is descope. That's the jargony way we talk about bad things happening to spacecraft. We descoped our rock abrasion tool and really just assigned that manpower to making sure our drill works. So we have the sampling system unlike anything that's ever been flown to any planet, especially without a human there to clean it and operate it. We have a sampling system that's capable of jackhammering into rocks, acquiring powder from those rocks, and delivering it to our laboratories on board the rover. And so that accomplishes some of the same goals as the rat in the sense that you're getting 5 centimeters into the rock and actually throwing out that first centimeter. The drill isn't capable of even getting that first centimeter material, so we will be, by definition, only sampling the parts below that outer weathered surface. So we thought it was a good trade when we ran into really a limitation of personnel to make sure this entire sampling system made it to Mars in 2011.
I think that Viking was playing Russian roulette when it came to the surface of Mars. It hit a rock that was curtains for it. Now, I suppose you guys have developed, and I think you might have said something about it, but I didn't detect it, something that would prevent you from landing on a huge rock and ruin everything. And I was just wondering, what kind of a mechanism is it, and how difficult was it to capture those images and guide the spacecraft to some other places, if in fact you're doing that?
Yeah, I'll give you the bad answer or the good answer. The bad answer is that we're actually not doing what you call hazard avoidance during landing. So the spacecraft flies itself down to the surface sensing the atmospheric conditions. It senses the weather, basically our inability to perfectly predict the weather. It can sense whether it's too dense or not dense enough, and then kind of pull up on the stick or push down on the stick. That's pretty awesome, you know, but then in its final stage of descent, it doesn't do anything to make sure it's not landing on a slope or a rock that could kill it. The reason this is a trade, the reason we chose not to spend resources in putting that kind of technology on the mission is because we have HiRISE. Now, HiRISE is basically a spy telescope on the Mars Reconnaissance Orbiter. You know, we can see rocks that are this big across. Just 30 centimeters is the resolution of that camera. So we've literally, and by we I mean graduate students everywhere, we've literally counted thousands and thousands of rocks at each of our landing sites that we chose to send this, that we were considering to send MSL. And so we've counted the rocks. We've determined if then the probability of, you know, you can statistically calculate in this 7x20 landing ellipse, what are your chances that one of your wheels will end up on a rock that's bigger than it can tolerate? And we've chosen sites where the percentage of that failure is down much less than 1%. So Gale Crater is a nice place because it really is basically a rock-free surface. It does have some slopes and ridges, but they're kind of on the 1 meter scale next to this mountain, which we would never dare land on, but at least the flat plains around the mountain are safe.
Spacecraft lands is going to be suspended on cables, is that correct? Is that a serious potential failure for that?
Yeah, the question is, he was noting our sky crane phase of the descent, which is, well, there's actually multiple terrifying aspects of the descent, that being the latest one. So at the very end, about 60 feet off the ground, there's the rocket-powered descent stage that has 8 rockets firing, and then the rover is lowered down from that descent stage, starting at about 60 feet and then continuing. It's not a hovering thing, which is often a misconception. We never hover. We just start lowering the rover down as the descent stage is reaching the surface, touch the rover down at about 1.5 miles an hour, and as soon as that touchdown is sensed, the cables are cut and the descent stage throttles up, flies away, and crashes. Now the question was, is that a potential source of crashing or failure? Certainly, just like all the other parts of the descent. But I'll tell you why we chose it, because that is a question that often comes up. You know, why didn't you use airbags again? The funny thing with that is, you know, airbags in 2004 were considered the untested, how can you believe this is ever going to work? And now they're considered the safe thing. But we have a 900 kilogram rover, so 2,000 pounds, which is 5 times as heavy as the Mars exploration rovers. And the airbags, we couldn't find material that would be strong enough to absorb that. And then when you think of enclosing that large vehicle and the amount of airbag material, it becomes as heavy as the rover itself. So then another option could be landing it on a pallet, a platform, or legs. You have a couple problems with that. Again, the pallet to absorb a 900-kilogram rover on top of it would also be a huge mass to carry all the way with you and launch from Florida, et cetera. On legs, it's even worse because now you're putting that huge, heavy rover above the ground, and making its center of mass, above the ground and causing an instability. There's yet another thing, which is that landers such as Phoenix and Viking and Apollo, for that matter, have to deal with an issue when, right as you're coming down to the surface and your rockets are, these are extremely high velocity plumes coming out of the rockets, they get near the surface, they start excavating dirt, they start forming, especially on a planet with an atmosphere, forming this turbulence and causing a lot of instability. And if you don't cut those engines off precisely when you touch down, then of course you're even in a worse state because you could do something else. So this was a problem with the Mars Polar Lander, for example, where the touchdown sensors are so hair trigger that it actually triggered 80 feet above the ground because of some other mechanism that was being deployed, and the Mars Polar Lander fell the last 80 feet, after a 100 million mile journey. So all these reasons make the sky crane actually a safer way to do it. You are putting, instead of having to carry the platform with you, you're using a descent stage, which is really just a little bit of a metal skeleton with these 8 rockets. So you save a lot of mass by putting the platform above you instead of below you. You keep the rockets many tens of feet above the ground. They never interact with the surface. And then also, very interestingly, I thought this was really cool. You touch down the rover, and the descent stage keeps going, and it senses the weight of the rover being released from those tethers. And actually, you have 2 seconds to sense that. That's an eternity when you're deciding whether to shut off your engines or not. And so they have 2 full seconds to make sure, are we on the ground? Yes. Are we on the ground? Yes. And then you cut the cables and you fly off. So hopefully you're a little bit more convinced that this might actually work.
Time for one more question. Guy at the back of the white top. No, you.
One more question. So methane is believed to be detected on Mars based on telescopic observations at certain concentrations. How does the sensitivity of your instruments compare to these concentrations? Will your sensitivity be just about at the noise level, or would there be a clear spike assuming these concentrations are present?
Yeah, good question. And methane, that's an interesting one too, because we didn't plan to do a big methane campaign in 2004, but then it was discovered, and it became, we actually changed the SAM instrument to be more sensitive to methane. So we would have something to say about the possibility of methane. Now, methane's been detected spectroscopically from Earth and from a spacecraft at Mars, the Mars Express. We'll be able to look at it in one location, of course, on the surface, not the whole planet. But when we first make a SAM measurement, when we first ingest the air from Mars, it'll probably be only a month or so into the mission. This is one of the first things we want to do, because we're going to take more time, of course, to drive to the mound and to deploy the arm and drill. All that's going to take a few months to get going. But one thing we can do very quickly after landing is suck in some air and analyze it. So when we run SAM the very first time, the detection will probably be something like at the noise level. But when we run SAM in a mode later on that's specifically designed to concentrate the methane before detecting it, using standard kind of chemistry, analytical chemistry techniques, then we'll get a whopping signal if it's at the amounts that are claimed by the Earth observations. It's interesting because there's people who think the Earth observations are not correct, that they're actually seeing methane in the atmosphere of Earth instead. There's also then the implication for life. And again, getting back to the very first question, we'll look at the isotopes of the methane to see if it's especially light or heavy. But again, we don't know what the baseline is. So you'll watch this unfold, and there'll be lots of vigorous science discussion, but that's why we do these things. Yeah.